Hello, everyone, and welcome to my PhD defense. The title of thesis is quite long. Let's see what the thesis is about. It is about road-heavy vehicles, which are powered by internal combustion engine using diesel fuel or by batteries using electric energy. They come in different sizes, driven by humans or by automated driving systems without human drivers. And electric-driven axles are allowed in any unit of these vehicles. These vehicles are designed in relation to the infrastructure and operational environment. And infrastructure include charging stations and loading and unloading schemes. Moreover, this thesis considers optimal control of energy of these vehicles, where vehicles are aware of road elevation in front of them, and decide optimally the velocity, optimal state of charge, optimal gear ratios, and transmission ratios. Moreover, the vehicles are aware of the coordinates of the road, and they plan the distribution of the forces between axles for each of the individual axles with the purpose of motion control combined with energy management or separately. The main research questions can be formulated as follows. How the efficiency and profitability of the road freight transportation can be improved when we allow electric derivatives on any unit of the vehicle? And how is the fleet vehicles propulsion optimization is coupled with the operational environment and infrastructure? Also, how can the longitudinal and lateral motion of these vehicles be optimally controlled, considering the minimum energy usage and safety? These questions apply to both vehicles with human driver and without human driver, driven by automated driving systems. Answer of these questions help us to enhance road freight economy, transport, and energy efficiency and road safety, which are the motivations of this work. Why enhancement of road freight transport economy is important? Road freight transport is responsible for about 75% of land transport in Europe, which is increasing. This increasing demands, together with pressures from regulators to fulfill environmental standards and increasing customer expectations and availability of new technologies, create a competing market, while they are in contradiction to reducing the cost of vehicles. On the other hand, having efficient and profitable, cost-efficient and profitable businesses and vehicles are the priority here. So vehicles can be successfully accepted into the market if they show less costs and cheap. Two important compounds and sources of future revenue growth in truck industry include new technologies and freight volume growth, and competitiveness of new transportation solutions depend on development and implementation of new technologies. And these new technologies include vehicles without human driver, driven by automated driving systems, electrification and alternative powertrain and fuel with low prices, and also implementation and using longer and heavier vehicles in the transportation. Longer and heavier vehicles are good for a wide range of transportation assignments, and they are cheap and efficient per unit freight transported. There were two case studies performed in this thesis to demonstrate why longer and heavier vehicles are important and good. For example, in the left case, we see a small vehicle. Most of the lifetime, this vehicle is standing still because it works in a short route with a long loading and unloading time. Therefore, the utilization is low. And when the utilization is low, a vehicle with low investment is the best choice, which is a small vehicle in this case. In the right case, the vehicle spends most of its lifetime on roads with quick loading and unloading. Therefore, there is a high utilization. And for high utilization, a vehicle with lower operational cost is the best choice, which in this case is a longer and heavier vehicle. Moreover, heavy vehicles contribute to about 25% of production of emission in Europe in 2016. And the target set by European Commission is to reduce this emission by 15 and 30% before the years 2025 and 2030. Moreover, these emissions are increasing because of increasing traffic. Therefore, implementation of new transport solutions are important. Also, the dynamic motion of heavy vehicles and multi-trailer vehicles are different from passenger cars because they are heavier, longer, and they have articulation joints. And also, the critical situations created by these vehicles are more serious and different. Moreover, the dynamic motion of the longer and heavier vehicles are different from tractor semi-trailers, as can be seen in right animation, where a large off-tracking happens during a lane change maneuver by this vehicle, where we see that the last part of the vehicle goes out of the road, which might not happen for a tractor semi-trailer. That emphasizes the importance of developing new control strategies to avoid this situation. To solve these problems and to answer the research questions, this thesis used mathematical models and optimization methods. Mathematical models included total cost of ownership, models for multi-trailer vehicle lateral and longitudinal motion control, and simulation. Also modeling for powertrain, models for powertrain, charging and battery state of health, operational environment, and operating cycles. In the thesis, there were a series of optimization problems solved. They included minimization of total cost of ownership, which were solved using derivative-free optimization because the cost is non-smooth and non-linear, and the design variables are discrete. Also, non-linear optimal control methods were developed for energy and motion control, which were solved by using direct optimal methods and by converting them to linear programs, non-linear programs, and mixed integer nonlinear programs, which were solved then by sequential programming. Also, for several problems in the thesis, dynamic programming has been used. The total cost of ownership here includes operational and depreciation costs. Operational costs included diesel fuel, electric energy, driver, vehicle maintenance, taxes and insurance, discount rate or interest, transportation emission management system in case of driving automation and vehicles without human driver. Also, the depreciation of purchase price included vehicle chassis and powertrain components, as well as investment of infrastructure. TCO calculation also included the economic lifetime, rest value, which were different for different components of the vehicle. For example, for the last replaced battery, which might have a better state of health, the rest value were different. Vehicle dynamic motions also needed to be modeled. In this thesis, vehicles with 1 and 2 track models were used. The important thing that need to be captured, the important dynamics were actually coupled lateral and longitudinal dynamics with nonlinear effect of combined slip tire models, which were needed for combined control, optimal control of lateral motion and longitudinal motion. As we can see in the right figure, there is a schematic of these figures, 2 track and 1 track, where 1 track is simpler and shows very close dynamics to the 2 track models. This resulted in very large differential algebraic equations, which were validated using measurement data, and the measurement data were obtained by using this vehicle, which is an A-double consisting of tractor, semi-trailer, dolly, and semi-trailer. The simulation results and measurement results showed very close relationship, and here you can see an example of a yaw rate for different units in a braking curve maneuver, which they are quite in close relationship and acceptable for our purpose in this thesis. Moreover, thesis needed to develop powertrain models for powertrains, which included conventional battery electric or hybrid. And here you see a schematic of the parallel hybrid powertrain. Each subsystem of the powertrain has its own power losses and energy losses models. For example, we use here efficiency, which were measured for these components for the internal combustion engine and electric motors, together with limits on the torque as a function of speed of these components, which were used for evaluating the power loss. Also, operational environment and operating cycles need to be modeled, which include a transportation network roadmap, which consists of routes, customer locations, and topography of routes, including elevation and coordinates, and the curvature, which were obtained either by direct using the available maps or by performing measurements. So a well-stated problem is a half-solved problem. If we have good description of the system dynamics and operational environment, and we know how to solve the nonlinear optimization problems, then we can handle a series of different optimization problems with different cost functions and constraints. The challenge is, however, how to handle them efficiently and in a real time, if they need to be handled in real time. As an example, we see an optimization problem here, which tried to answer the first two questions, which is integrated vehicle infrastructure design. The first two research questions were how to improve the efficiency and profitability of the transportation solution using electrification, and how it is dependent or it relates to the infrastructure. Here, the design variables are vehicle types and vehicle components and infrastructure. The vehicle components included choice of powertrain source of power, for example, conventional full electric or hybrid, and then the size and type of electric motors and their location and number of driven axles, type and size of batteries and size of the internal combustion engine. And the infrastructure included charging stations and loading unloading scheme in each of the node of the transportation network. The objective is to minimize total cost of ownership, and the constraints are vehicle model constraints, which include system dynamics, powertrain limits, and performance constraints, which set a minimum requirement on the torque and power of these vehicles, for example, for handling the required startability and gradability, and transportation task constraints, which ensure fulfillment of the demands of freight pickup and delivery in each of the transportation network nodes and customer locations. This vehicle infrastructure optimization problem was solved for different scenarios to understand the competitiveness between different transportation solutions. These different scenarios varied in, for example, the type of the source of power, conventional or battery electric, the size of the vehicles, and if they are driven by humans or by automated driving systems without humans, and also parameters of the driving cycle, for example, the length of the route, the hilliness of the route, and the optimal speed. Also, relative sensitivity analysis were performed against contributing factors such as the price of the fuel, price of the electric energy, and the price of the battery and others, which resulted in generation of a very large data, which then were used for studying the competitiveness between different transportation solutions. As an example, using the analyzed data, we show here why longer and heavier vehicles are important and good. Assume that we have a vehicle with, we have 4 types of vehicles with different sizes. The first one is a rigid truck, tractor semi-trailer, Nordic combination, and the last one is A-double. Assume that we have enough load to fill the first vehicle, the smallest one, which is a rigid truck, and the other vehicles are partly filled. In that case, the smallest vehicle shows the lowest total cost of ownership per unit for transport. But also assume that we have enough load to fill also tractor semi-trailer. In that case, the total cost of ownership per unit freight transported suddenly drops. And this is because basically we transport twice more freight, but with a slightly increased cost of operational cost and investment cost. And further, if we have enough load to fill the other vehicles, as larger the vehicles becomes, there is a more drop in the total cost of ownership. As you can see here, that the A double shows the lowest total cost of ownership. A reduction of 20% compared to tractor semi-trailer, and a reduction of 43% compared to the rigid truck. So if we assume this, we have 100% capacity utilization, and if we assume that these vehicles work day and night, here is a comparison between different contributing cost factors. We see here the cost of the driver in a red color, and then fuel in yellow, and maintenance in brown colors. So these are operational costs, which form the great part of the total cost of ownership. And the depreciation of the investment cost in these vehicles, because conventional vehicles with human drivers actually form a small part of the total cost of ownership, which makes these vehicles a bit insensitive to utilization. If we add electrification, if we electrify these vehicles, we replace the cost of fuel by cost of batteries and charging infrastructure and electric energy, then we add to the cost of investment, and we reduce the operational cost. In that case, it makes these vehicles more sensitive to utilization. And also we see that for this particular example, which is the road with 80-kilometer length, the electric vehicles cannot beat the conventional vehicles unless the cost of infrastructure is removed from TCO calculations. Moreover, there is a misconception, usually stating that electrifying the big vehicles is not good because they need big batteries. This is basically true only for transportation with low utilization. If we have high utilization, actually big vehicles needed smaller batteries per unit freight transported, as can be seen here. So what happens if we automate these vehicles? So we remove the driver cost and replace the transportation mission management cost and cost of equipment. And if these vehicles are highly utilized, then the cost of automation is less than drivers, and these automated vehicles become more competitive. And if we automate the electric vehicles, there is also a reduction in cost, and this reduction is higher for electric vehicles compared to the conventional vehicles. And it is due to more efficient driving, which requires smaller batteries, and also smaller batteries because we don't need batteries for driver equipment, driver-related equipment such as heating and so on. But also we added to the investment cost, and we reduced the operational cost. So these vehicles show different sensitivity to utilization, which is a very important factor here. If we have 100% utilization, electric vehicles without human drivers show the lowest cost. If we reduce utilization, then it is conventional vehicles with automated driving system that show the lowest cost. And if we reduce further the utilization, there are actually conventional vehicles with human drivers that show the lowest cost. That shows that different transportation solutions are really sensitive, show different sensitivity to utilization, and also other cost factors. For example, cost of batteries and electric energy and fuel. And all these data were analyzed, and the comparison of different cases are provided in the published papers. And these data help us to answer different questions about the transportation solutions. For example, which size is good for a given transportation, and and if it's good to automate it or electrify it, and what is the sensitivity to contributing factors. So this was the example when we actually optimize a single vehicle. This problem can be extended for a fleet of vehicles when we can perform integrated fleet vehicle infrastructure design. Here, the solution is optimized fleet infrastructure, which was performed for a small transportation network in this thesis, because the optimization problem is very, very large with billions of possible combinations. Here, the fleet comes with vehicles of different sizes and numbers, and also different powertrains, which work in optimum missions that were found by solving the optimization problem. And also the location of charging the station and charging power, and the loading and unloading scheme, as well as the number of trips each of these vehicles need to perform to satisfy the transportation demand of all the network. Here is an example why coupled optimization of fleet vehicle and infrastructure is important. Assume that we have only a single vehicle in our fleet, then optimizer sees that it is better to have a vehicle with large battery size rather than having a fast charging stations, because it is cheaper. But if we have two vehicles in the fleet, then suddenly the fast charging stations become viable, and then vehicles can have a smaller size of batteries. And this clearly shows the relation between infrastructure design and vehicle powertrain design in case of electric vehicles. So we have seen that long and heavier vehicles are good for a wide range of transportation assignments. And in these vehicles, distributed propulsion on different axes may appear for the sake of energy efficiency and increasing of the power. But this kind of design creates a critical situation in some parts of the road. For example, the rear units might push the front units, or the brake forces might not evenly distributed because for the sake of energy efficiency. And the critical situation needs to be handled. And this comes to the third research question, which is how to optimally control the motion, longitudinal and lateral motion of these vehicles to assure safety and also energy efficiency. For that, nonlinear optimal control problems were defined in this thesis. The unknown design variables were trajectories of power of engine and electric motors, transmission ratios, forces on different axes and steering angles, depending on the problem in hand, with a cost function which included fuel consumption, for example, or electric energy losses in different parts of the powertrain, battery degradation, engine on-off, deviation from a desired path, also depending on the problem studied. And here, the constraints include system dynamics, powertrain limits, and trip time, and possibly others, also depending on the problem studied. So what is predictive energy management, basically? Predictive energy management is about using the information about the future of the transportation or future of the road to control the vehicle now. For example, to avoid unnecessary braking, or to save the electric energy and use it later when it is really needed. Here, a part of the driving cycle is shown where the horizon is about 8 kilometers, and the energy management sees these 8 kilometers and plans in real time the optimal vehicle velocity and gear ratios and state of charge. And this should be done when we limit also the speed of the vehicle based on the legal speed of the road or possibly curvatures to reduce the lateral acceleration. What happens if such a limit is not considered, if we don't reduce the vehicle speed based on the curvature of the road and based on the lateral acceleration? Critical situation might happen, as shown in this animation, which is rollover. Here, the subject vehicle is an A-double, which is driven in the second axle of the third unit, which is dolly, and the first unit is driven by conventional engine. So is it enough to limit the speed only based on lateral acceleration and curvature of the road? Here, another case is shown where vehicle is speed of the vehicle is limited based on the curvature during predictive energy management. But we still see that a critical situation happens and vehicles become unstable and the dolly and the last semi-trailer goes out of the road. This happens because optimal energy management sees that it needs to reduce the speed by using regenerative electric braking of the dolly. But then this happens because of complicated nonlinear properties of the tires. Basically, if you brake in X direction or in longitudinal direction, you lose the force in Y direction or in lateral direction. That's why the tire cannot tolerate the lateral force and it goes to the right and the vehicle becomes unstable. Therefore, non-linear properties of the tire combined slip need to be also taken into account during the optimal energy management. For example, the total force need to be limited and we need to make sure that the total force, for example, stays in this yellow ellipse shown in this top picture. And then also considering the combined slip effect. Here is shown the relation between lateral force and longitudinal force. And controller should make sure that the forces always stay in a green region, which is a constraint region for the whole horizon or part of the horizon. So this is included now in our optimal energy management, and vehicle is aware of the curvature on the road in front of it and reduces the speed by optimal distribution of the forces between different axles, considering the energy efficiency and safety of the vehicle. Here, unstable situation does not happen. And the blue part of the road is the horizon where the constraint on lateral stability is checked in advance. This is a new result when lateral stability constraints are included. We see in the first part of the horizon, which is about 400 meters, these constraints are active and it causes a reduction in speed and by distribution of the forces between axles. Here, an example is shown for the lateral force trajectory of the driving axis of the dolly. We see in the first case, with the blue curve, which is the lateral force, is in an unstable region. For stability, this curve should stay in a white region. And the force of the electric motors should not reach this pink area. In the second case, when these are included in optimal control management, the trajectory stays in the white region and makes the vehicle stable. Here is another example, which actually is minimization of off-tracking without the concerns of energy efficiency. Here, the objective is to minimize off-tracking by using nonlinear model predictive control, similar as before, with combined steering, braking, and propulsion control, and by optimal distribution of the forces between axles, where here the dolly is also steerable, and the vehicle is aware that it's going to change the lane and plans these forces in an optimal manner in order to ensure safe motion and reduction in off-tracking. So this thesis resulted in several publications and 2 patent applications. And the main contributions are listed in this slide. This thesis tried to develop methods for increasing the road freight transportation efficiency and profitability by designing vehicle propulsion system coupled with infrastructure design and operational environment. Also, the thesis demonstrated the relation between automation and electrification in different transportation assignment and scenarios, and also identified the zero emission profitable solutions. The thesis tried to develop methods for predictive longitudinal and lateral motion control of multi-trailer vehicles by combining steering, propulsion, and braking in long horizons. And also development of methodology for controlling of the motion of the vehicles, considering the energy usage of multi-trailer vehicles, and in a predictive manner, considering lateral stability. And the main conclusions are that there is a coupling between vehicle hardware optimization design, routing, logistic, and infrastructure, and they need to be handled in an integrated manner. And also profitable, efficient, and safe road freight transportation can be achieved by optimizing the vehicle and infrastructure and simultaneous optimal control of energy usage and vehicle motion on roads. So it was all, and thank you for listening.